All right, today we're diving into one of the most sneaky and frustrating problems in all of system design. It's that feeling when everything looks fine on the surface, but deep down, you know nothing is actually getting done. We're talking about deadlocks, livelocks, and starvation. You can think of them as the silent killers of progress.
You know, when you think about a system failure, what comes to mind? Probably a big crash, right? Error logs just scrolling endlessly, alarms blaring. But what if none of that happens? What if the system just goes completely quiet? So you look at your monitoring dashboards and everything's green. CPU usage, totally normal. Memory, rock solid. There are 0 error messages, no exceptions being thrown anywhere. I mean, by all accounts, the system looks perfectly healthy. And yet, the work has just stopped. Requests are timing out, data isn't flowing. The system is technically alive, but it's not doing anything useful. This is the exact mystery we're going to unravel today. We're going to figure out why this happens, and more importantly, what we can actually do about it. Okay, so here's how we're going to break this down. First, we'll look at the problem of progress itself. Then we'll meet our 3 main culprits: deadlock, livelock, and starvation. After that, we'll talk strategy, how to fight back, and we'll wrap it all up with a really crucial takeaway about system design. All right, first up, the problem of progress. So where do these bizarre failures even begin? Well, it all starts with a super common and totally necessary setup in almost all modern computing. The whole problem kicks off when you have multiple things, let's call them agents or processes, all trying to grab the same limited resources. Think database connections, files, you name it. And here's the kicker. There's no central traffic cop telling everyone whose turn it is, so they just get in each other's way. And this is so important to understand. These aren't just simple bugs you can patch. No, these are fundamental failures at the design level of the system. Okay, let's meet our first culprit. Probably the most famous one of the bunch, deadlock. You can think of it as the master of gridlock, a complete and total standstill. So what is a deadlock technically? Well, it's a state where a couple of processes get stuck in this vicious circle of waiting. Each process is holding on to a resource that another one needs, and nobody is willing to let go.
Okay, here's the classic textbook scenario. Imagine process A grabs lock 1. At the exact same time, process B grabs lock 2. Now, process A needs lock 2 to move forward. But process B has it. And what does process B need? You guessed it, lock 1, which process A is holding on to. They're stuck. They will literally wait for each other forever. And boom, total gridlock.
Now, it turns out, for a deadlock to even be possible, 4 specific conditions all have to be met at the exact same time. They're often called the Coffman Conditions. Basically, it means resources can only be used by one process at a time, processes can hold a resource while waiting for another, you can't just snatch a resource away from a process, and of course you have that circular wait we just talked about. But here is the golden nugget for engineers. You only have to break one of these 4 conditions. Do that, and you make deadlock completely impossible in your system. All right, next up we've got Livelock. Now this one's a bit more deceptive because it looks like stuff is happening, but it's all just wasted motion. That's why I think of it as the overly polite saboteur. So what's the real difference here? It all comes down to activity. With a deadlock, everything is frozen. The processes are blocked, they're just waiting. But in a livelock, the processes are super active. They're constantly changing state, responding to each other, but they're not making any forward progress. It's exactly like 2 people in a narrow hallway. They both try to be polite and step aside, but they both step the same way. Then they step back the other way, together again. They're moving, but they're getting absolutely nowhere. And that brings us to our third and final culprit, starvation. Now, this isn't about a system getting stuck in gridlock or spinning its wheels. This is about something more fundamental, plain old unfairness. Starvation is what happens when one poor process just never gets the resources it needs to do its job. Why? Because other, maybe higher priority or just luckier processes always jump the queue and get served first. The system as a whole is chugging along just fine, but this one process is left behind completely starved, never getting its turn. And the really scary part, your monitoring tools probably won't see a thing. Starvation is often totally invisible until you get that dreaded phone call from a user saying, "Hey, my stuff is never finishing." Okay, let's pull all this together and look at them side by side. It's actually pretty clear when you see it this way. Deadlock. No activity, no progress, all because of that circular waiting. Livelock. Lots of activity, but still zero progress, thanks to that constant overreaction. And finally, starvation. Yeah, there's activity and some processes are making progress, but it's all rooted in unfair scheduling. The key takeaway? All three are progress failures, not crashes. So we've met the villains. The question is, how do we fight back? Well, the good news is engineers have come up with a whole toolkit of strategies to build our defenses and stop these stalls before they start. When it comes to preventing deadlocks, one of the most powerful tools is lock ordering. Just make sure every process tries to acquire locks in the exact same sequence. If you do that, a circular wait just can't happen. Another great one is timeouts. If a process is waiting too long, it just gives up and tries again later. And for the really high-performance stuff, you can even use clever lock-free algorithms that avoid the whole problem entirely. And for Livelocks, the name of the game is breaking that cycle of endless, polite retries. Remember the two people in the hallway? The solution is to introduce a little bit of randomness. A random back-off delay before trying again is a super common and effective trick. It breaks the symmetry and lets one process go first. Finally, to stop starvation, you have to bake fairness right into your system scheduler. A really cool technique for this is called aging. The idea is simple. The longer a process waits, the higher its priority becomes. It's like letting someone who's been waiting forever cut to the front of the line. It guarantees that eventually, everyone gets a turn. And all of this really points to a core philosophy in engineering. You see, while you can build complex systems to detect these problems and try to recover from them, it is always better and cheaper to just design your system so they can't happen in the first place. An ounce of prevention is worth a pound of cure, right? Okay, let's zoom out for the big picture. Why should you care about all this? Because these are not some obscure academic problems. No way. These failures happen in the most critical systems we all depend on every single day. I'm talking about everything, from the operating system on your laptop to the giant databases that run your favorite social media apps. We're talking massive cloud platforms, the very network protocols that make the internet work. All of these incredibly complex systems are vulnerable to these kinds of progress failures. You know, a surprising number of major outages you hear about aren't actually crashes, they're coordination failures, just like these. And this all leads us to the final, and I think most powerful insight of this whole discussion. You can have a system that is perfectly coded, blazing fast, and by every metric you have, totally stable, and it can still fail. It can fail completely at its one true purpose, making progress. So here it is, the big takeaway. Progress is not an accident. It doesn't just happen on its own. It is a fundamental design responsibility. If you don't actively and consciously design for fairness and coordination from the very beginning, your system will, eventually, grind to a halt. It's not a question of if, but when.